China keeps coming back to the moon, quietly, methodically, relentlessly. While other space programs chase headlines and celebrate single launches as if they were the culmination of human ambition, China has been executing a plan that was drawn up over 2 decades ago, and they have never once deviated from it. Not a single mission wasted, not a single step skipped. What they are building, step by step, mission by mission, module by module, is something the world has never seen before. And if you understand what they are actually after, the scale of it becomes almost difficult to comprehend. This is not a story about rockets. It is not a story about national pride or geopolitical one-upmanship, although those elements are certainly present. This is a story about the moon itself, about what it contains, what it can provide, and why whoever figures out how to permanently occupy it first will hold a card no other civilization in human history has ever held. The moon is not just a destination. It is a platform. It is a way station. It is a key. And China appears to be the country most systematically working toward picking up that key and using it. Let us start at the beginning. Back in the early 2000s, when most of the world's attention was consumed by events on Earth, Chinese scientists and engineers were quietly laying the groundwork for one of the most methodical space programs in human history. They devised a multi-decade roadmap that was not organized around spectacle. It was organized around knowledge, around infrastructure, around the kind of long-game thinking that is extraordinarily rare in any human institution, let alone one as expensive and politically sensitive as a national space program. The plan was divided into 4 distinct phases. First, orbit the moon and map it in unprecedented detail. Second, land on the moon and begin surface exploration. Third, collect samples of lunar material and return them to Earth for laboratory analysis. Fourth, establish a permanent human-capable installation on the lunar surface. Each phase had to be completed successfully before the next could begin. There were no shortcuts. There were no parallel tracks that collapsed into each other under political pressure. Each mission was designed to deliver the precise knowledge required for the mission that followed it. Think about what that actually means. In an era when space agencies around the world routinely cancel missions mid-development, shift priorities based on electoral cycles, and abandon infrastructure because budgets fluctuate, China has been executing a continuous, unbroken chain of increasingly complex lunar operations for nearly 2 decades. That is not luck. That is institutional willpower of a kind that is genuinely unusual in the modern world. The analogy that comes to mind is not a race. It is construction. If you are building a skyscraper, you do not install the windows before the steel frame is complete. You do not begin the roof before the foundation has cured. You do not move furniture into the upper floors while workers are still pouring concrete on the lower ones. Every step has a logical predecessor. Every phase exists because the one before it made it possible. China's lunar program works exactly this way. The first mission, named Chang'e, one after the ancient Chinese moon goddess, launched in 2007. The name is poetic. The mission itself was anything but. It was precise, disciplined, and almost aggressively utilitarian. Chang'e 1 spent more than a year in lunar orbit, using an array of instruments to produce the most detailed topographic maps of the moon that had ever been created. No dramatic landings, no human stories, no television-friendly moments of wonder. Just clean, accurate, extraordinarily valuable data that scientists and engineers could study for years, gradually transforming it into the foundation for everything that would follow. 3 years later, Chang'e 2 built on that foundation and pushed it further. Its mapping resolution was dramatically higher, allowing researchers to examine individual craters, ridgelines, and boulder fields with the kind of clarity that had previously been impossible. For mission planners, this was critical information. A lander that touches down on a slope that is too steep will tip over. A rover that drives into a field of loose regolith that looks flat from orbit may sink and become immobilized. The difference between a successful surface mission and an expensive failure can come down to terrain features that are invisible at lower resolution. Neither of these missions made front pages. They were not the kind of space exploration that generates social media content or inspires documentaries. But behind the scenes, they were doing something that no amount of engineering can replace. They were generating certainty in an environment defined by uncertainty. They were building the map that every future mission would use to navigate, and what came next would put that map to use in a way that shook the scientific community. In 2013, China executed its first genuinely transformative mission. The Chang'e 3 lander became the first spacecraft to achieve a soft landing on the Moon since the Soviet Luna 24 mission in 1976, nearly 4 decades earlier. Think about that gap. 37 years during which no nation on Earth managed to gently set a spacecraft down on the lunar surface. And then, without fanfare, with almost surgical precision, China did it. On board was a small robotic rover named U2, Jade Rabbit in Chinese, a reference to the mythological companion of the moon goddess. U2 rolled down the ramp of the lander and onto the gray, powdery surface, and immediately began doing exactly what it was designed to do. Within days, it had found something unexpected. For decades, virtually everything humanity understood about lunar geology came from the Apollo missions. 12 astronauts had walked on the Moon between 1969 and 1972. They had collected hundreds of kilograms of rock and soil samples. Those samples had been analyzed continuously by scientists around the world ever since, producing an extraordinarily detailed picture of the Moon's composition, mineralogy, and geological history. Textbooks had been written. Models had been built. The consensus view was robust. We understood what the Moon was made of. Except we did not. Not really. U2's instruments analyzed the soil particles and rock samples in its immediate vicinity and found a volcanic rock type unlike anything in the Apollo collection. The chemistry was different. The mineral structures were different. It was not a variation on a known theme. It was a genuinely distinct category of lunar material. For planetary scientists, this was the equivalent of finding a recipe in a cookbook you thought you had memorized, only to realize you had never even seen the chapter it came from. What this discovery revealed was profound. The Moon is not a geologically uniform body. It is a world of extraordinary internal complexity, with regions that formed through different processes at different times in its history. The Apollo landing sites, spread across a relatively small portion of the Moon's near side, had given us a sample that turned out to be deeply unrepresentative. The Moon we thought we knew was only a sliver of the actual story. And if places we had already visited could still surprise us this dramatically, what could possibly be waiting in the regions we had never visited at all? The Moon is tidally locked to Earth. This is not a coincidence. It is the inevitable result of gravitational dynamics playing out over billions of years. The Moon's rotation rate matches its orbital period so precisely that one hemisphere always faces us, and one hemisphere always faces deep space. No matter where you stand on Earth, no matter how powerful a telescope you use, you will never see the far side of the Moon with your own eyes. For most of human history, the far side was simply an absence, a blank in our understanding that we could not even approach. The first images of it came from Soviet spacecraft in 1959. But actually landing there, that was another problem entirely. The moment a spacecraft touches down on the far side, it loses all direct line of sight communication with Earth. There is no way to send commands, no way to receive data, no way to know immediately if something has gone wrong. It is the equivalent of trying to perform surgery while blindfolded, in a room from which no sound can escape. China's solution to this problem was one of the most elegant pieces of mission architecture in the history of space exploration. Before sending the lander, they deployed a small relay satellite called Queqiao, Magpie Bridge, into a precisely calculated halo orbit at the Earth-Moon L2 Lagrange point, approximately 65,000 kilometers beyond the Moon. From this unique vantage point, the satellite could simultaneously see Earth and the lunar far side. It became a permanent bridge for signals, allowing continuous two-way communication between the spacecraft on the surface and mission controllers on Earth. In theory, the concept was straightforward. In practice, threading a satellite into a specific halo orbit with sufficient precision to maintain visibility of both Earth and a precise landing zone required calculations that left essentially no margin for error. Any drift, any miscalculation, and the entire relay system would fail. China executed it perfectly. In January 2019, Chang'e 4 descended into the von Karman crater within the South Pole Aitken Basin, one of the largest confirmed impact structures in the entire solar system. The basin stretches more than 2,500 kilometers across. To grasp that scale, if you place this single crater over Western Europe, it would cover everything from Portugal to Poland, from Scandinavia to the Mediterranean. Scientists believe the impact that created it may have punched through the lunar crust entirely, exposing material from the deep mantle below, rock that has been buried since the Moon itself formed. The scientific value of that location is almost impossible to overstate. Chang'e 4's rover, Yutu-2, has been operating continuously since landing and has far exceeded its designed operational life, becoming the longest operating lunar rover in history. It has found further evidence of mantle material exposed at the surface, confirming that the South Pole Aitken Basin is one of the most scientifically significant locations on any body in the inner solar system. Then, in 2024, China accomplished something even more audacious. Chang'e 6 did not just land on the far side. It landed, collected approximately 1.9 kilograms of ancient rock and soil from the floor of the Apollo crater within the South Pole Aitken Basin, sealed those samples inside a hermetically protected container, launched a small ascent rocket from the lunar surface, rendezvoused with an orbiting return vehicle in lunar orbit, transferred the precious cargo, and brought it back to Earth. Read that sequence again. Every single one of those steps had to work. A failure at any point, the sample collection, the containment, the ascent rocket firing, the orbital rendezvous, the sample transfer, the atmospheric re-entry, would have meant total mission failure. And this was accomplished on the far side of the Moon, where direct communication requires relay spacecraft, and where every operation adds complexity. The samples returned were approximately 2.8 billion years old. Analysis revealed chemical signatures of volcanic activity occurring far later in lunar history than most models had predicted. This single fact, that volcanic processes on the Moon were still active billions of years after the standard timeline, suggested they should have stopped, rewrote significant portions of our understanding of how the Moon evolved. It means the Moon's geological story is richer, longer, and far more complex than any textbook published before 2024 reflects. Each new sample, each new landing site, each new rover traversal adds another layer to a picture that turns out to be far more intricate than we ever suspected. But all of this, as remarkable as it is still not the prize. Picture a clear night. You look up at the Moon. Now mentally trace your gaze to its lowest point, the South Pole. On Earth, poles are defined by cold and ice. On the Moon, the South Pole is something far stranger and far more extreme than Earth's polar regions. Because the Moon's axial tilt is extremely small, only about 1.5 degrees compared to Earth's 23.5 degrees, sunlight arrives at the poles at a grazing angle, skimming along the surface rather than striking it from above. In this geometry, The high walls of deep craters can cast permanent shadows across the crater floor below. Not seasonal shadows, not temporary shadows, permanent ones. Some of these craters have not received a single photon of direct sunlight in billions of years. The last time sunlight touched their floors, Earth did not yet have multicellular life. The craters sit in what scientists call permanently shadowed regions, PSRs, and inside them, temperatures drop to around -200 degrees Celsius. That is colder than the surface of Pluto. It is, in fact, among the coldest natural environments anywhere in the solar system. And that extreme cold is precisely what makes them so extraordinarily valuable. Over billions of years, comets, asteroids, and interplanetary dust have delivered water to the lunar surface. On sunlit areas, that water immediately sublimates. It passes directly from ice to vapor and drifts away into space. But inside the PSRs, there is nowhere for it to go. It hits the frozen surface and stays. Layer upon layer, delivery upon delivery, accumulating over geological timescales. Orbital data from spacecraft, including India's Chandrayaan-1, NASA's LCROSS impact mission, and the Lunar Reconnaissance Orbiter strongly suggest that significant quantities of water ice are locked inside these permanently dark craters. Now think carefully about what water actually means in the context of space exploration. Water is H2O, 2 hydrogen atoms and 1 oxygen atom. Oxygen is what astronauts breathe. Hydrogen, when combined with oxygen and ignited, is one of the most powerful rocket propellants ever used. The Saturn V rockets that carried Apollo astronauts to the moon in the 1960s ran on liquid hydrogen and liquid oxygen. If you can mine water ice from the lunar South Pole, electrolyze it into hydrogen and oxygen, compress and liquefy those gases, you have both breathable air and rocket fuel, produced locally on the moon without shipping anything from Earth. This changes everything about the economics and logistics of space exploration. Right now, launching a kilogram of payload to the moon costs somewhere between $10,000 and $100,000 depending on the mission architecture. Every kilogram of water, oxygen, and fuel an astronaut needs has to be lifted against Earth's full gravitational pull, a force so powerful that modern rockets spend the majority of their propellant just reaching orbit. The moon's gravity is only about 1/6 of Earth's. Launching from the lunar surface requires a tiny fraction of the energy. A lunar fuel depot could supply missions to Mars, to the asteroid belt, to the moons of Jupiter, at a cost that makes those missions genuinely economically viable rather than once-per-decade financial gambles. The moon would not just be a destination, it would be a hub, a way station, the first extraterrestrial fueling station in human history. And whoever builds it first does not merely win a race. They gain operational leverage over the future of deep space exploration that cannot easily be replicated by anyone who arrives second. That is what is buried in those dark craters at the lunar South Pole. That is why China keeps going back. That is why the South Pole of the moon may be the most strategically valuable piece of real estate in the solar system. Confirming the presence and quantity of water ice in those permanently shadowed regions is not something you can do from orbit. You have to go inside. But this creates an immediate engineering problem. Standard rovers run on solar power. No sunlight means no power. Standard rovers also rely on relatively flat, predictable terrain. The floors of polar craters are anything but. They are strewn with boulders, crossed by sharp ridges, and in some cases inclined at angles that would immediately flip a wheeled vehicle. Send a conventional rover into a PSR, and you will likely lose it within minutes. China's answer to this problem is the centerpiece of the Chang'e 7 mission, currently scheduled for launch in 2026. This mission represents the most technically complex lunar exploration attempt China has ever undertaken, and at its core is a vehicle type that has never before been used in the history of planetary science: a small, hopping robot. Rather than rolling on wheels, this probe will use small thrusters to hop. to leap over obstacles, to navigate the chaotic terrain that would defeat any wheeled platform, and to actually enter the permanently shadowed craters and take measurements from inside. It is equipped with mass spectrometers, neutron detectors, and near-infrared spectrometers capable of identifying water molecules in the surface material and subsurface layers. It can go in, make its measurements, and come back out, something a conventional rover cannot do. The analogy that comes to mind: imagine trying to explore a deep, irregular cave. You could send a wheeled vehicle to the entrance and try to push it down the slope, hoping it does not get stuck or flip. Or you could send something that leaps, something quick, nimble, designed specifically for chaotic terrain. The hopping probe is the second option applied to planetary science. Chang'e 7 is not just the hopping robot. It is a complete integrated system. An orbiter will map the South Pole region from above and relay signals between the surface spacecraft and Earth. A lander will touch down on stable terrain near the pole. A separate rover will deploy from the lander and characterize the local geology, identifying the most promising access points to the PSRs. The hopping probe will then use those findings to plan its entries into the shadowed regions. 4 spacecraft, 1 mission, all operating in coordination, continuously exchanging data. If Chang'e 7 confirms large-scale water ice deposits in the South Pole craters, the implications will extend far beyond any individual scientific paper. It will be empirical proof that everything needed to sustain human life and power human rockets exists on the moon in harvestable quantities. It will be the moment when moon as way station transitions from theoretical argument to demonstrated fact. But confirming a resource and knowing how to use it are entirely different challenges. You cannot simply collect ice from a permanently shadowed crater, hold up a press conference, and declare that you have built a functioning lunar base. You need technology that can survive the complete absence of breathable atmosphere, the violent temperature swings between lunar day and night, a swing of more than 250 degrees Celsius, and the constant radiation environment. You need systems that can operate for months or years without regular human maintenance. And you need to figure out how to build things on the moon without shipping construction material from Earth, because no mission will ever be economically sustainable if it must deliver every brick, every beam, and every bolt from a planet that sits at the bottom of a deep gravitational well. This is the mandate of Chang'e 8, currently scheduled for around 2029. This mission is entirely dedicated to testing what scientists and engineers call in situ resource utilization, ISRU, the use of local materials instead of Earth-supplied ones. One series of experiments will test the heating and compression of lunar regolith, the gray, powdery soil that covers the entire surface of the moon, to produce solid construction blocks. Think of it as baking bricks, but instead of clay taken from a riverbed, you are using the material that happens to be lying everywhere you look on the lunar surface. If this works, those blocks could be used to construct landing pads that suppress the enormous debris clouds kicked up when rocket engines fire near the surface. They could be used to build radiation shielding walls around habitation modules. They could be used to pave roads for rovers, eliminating the need to drive continuously over loose regolith that behaves more like quicksand than solid ground. Another set of experiments will test the extraction of oxygen directly from lunar minerals. Lunar regolith is oxygen-rich, but that oxygen is chemically bound inside mineral structures, not present as a free gas. Extracting it requires either electrolysis of mineral melts at extremely high temperatures or other chemical reduction processes that have to work in vacuum, in low gravity, and without a team of laboratory technicians standing by to fix problems. Chang'e 8 will attempt these processes in the actual lunar environment, not in a simulated one back on Earth, because the simulation and the reality are different enough that real-world validation is essential. There are also plans to test a robotic 3D printing system that would use lunar regolith as feedstock to print structural components layer by layer, The concept is similar to additive manufacturing systems familiar from industrial applications on Earth, scaled up and adapted for vacuum operation. The goal is straightforward. Autonomous robots could pre-build walls, floors, and protective domes at a chosen construction site weeks or months before the first human crew arrives. The astronauts would land not in an empty wasteland, but in a partially prepared structure. If these technologies work on the Moon, not in a laboratory on Earth, but under actual lunar conditions, in actual lunar regolith, under actual vacuum and radiation and temperature extremes, then the equation changes fundamentally. The Moon stops being a place you visit with everything you need stuffed into rocket cargo bays. It starts being a place that partially builds and sustains itself. Everything that has been described so far, the orbital mapping, the farside landings, the sample returns, the water ice search, the ISRU experiments, has been building toward a single culminating objective. China calls it the International Lunar Research Station, or ILRS. This is not a temporary outpost. This is not another flag and footprints exercise. This is a design for permanent human presence at the lunar South Pole, a complex of interconnected modules capable of supporting scientific research, resource extraction, manufacturing, and eventually long-duration human habitation. The current plan calls for construction to begin in earnest in the early 2030s. Initial robotic missions will pre-position power generation equipment, likely solar arrays for sunlit areas combined with small nuclear reactors for periods when solar power is unavailable, along with telecommunications infrastructure, scientific laboratories, and the first structural modules. Robots will do the most dangerous and physically demanding construction work before any human is asked to set foot in the environment. Gradually, over the course of several years, the station will grow, module by module, capability by capability. The first human visits will be brief, a few days, perhaps a week. But they will be the proof of concept, the dress rehearsal, the demonstration that a crew can survive the transit, function in the lunar environment, and return safely. Each subsequent human mission will be longer. The infrastructure will be more developed. The local resource utilization systems will be increasingly operational. China has actively invited other countries to join the ILRS, and the response has been notable. As of 2025, more than 20 national space agencies and research institutions had signed cooperation agreements with the ILRS framework, including Russia, Pakistan, the UAE, Venezuela, South Africa, and a growing list of others. The station is explicitly designed as a multinational endeavor, with China providing the foundational architecture and partner nations contributing experiments, technology, and personnel. This is a significant strategic move. It means the ILRS will not be seen by the international community purely as a Chinese installation. It will be a shared platform, one that China designed, China funded at the core, and China controls the operational parameters of, but one in which dozens of countries have a stake. And that gives it a very different kind of political and scientific legitimacy than a purely national project would carry. No lunar base plan is more credible than the launch vehicles and spacecraft designed to execute it. China has been testing both, and the results have been significant. The Changzheng 10, Long March 10, is China's next-generation crewed lunar launch vehicle. Capable of delivering approximately 27 tons to translunar injection, it is designed specifically to support crewed lunar missions within a two-launch architecture. In early 2026, the rocket successfully completed a critical low-altitude test flight, validating key systems before committing to the full orbital development program. The Mengzhou spacecraft, literally dream vessel, is the crewed vehicle that will carry astronauts to lunar orbit and back. It has completed critical emergency escape system tests, demonstrating that the spacecraft can reliably rescue a crew if something goes catastrophically wrong during launch. one of the most critical safety certifications for any crewed system. The mission architecture for China's first crewed lunar landing will require 2 launches, one carrying the crew in Mengzhou, one carrying the lunar lander separately. The 2 will rendezvous in lunar orbit, dock, and then 2 astronauts will transfer to the lander and descend to the surface, while a 3rd remains in the orbiting Mengzhou. After their surface activities, initially just a few days, they will ascend, rendezvous again, transfer back, undock, and return to Earth. This is essentially the same architecture that carried Apollo to the Moon over half a century ago, adapted with modern technology and executed at the end of a systematic 2-decade buildup rather than a desperate sprint driven by Cold War competition. The first crewed landing is currently targeted for before 2030. China has stated this publicly. NASA's Artemis program, which originally targeted a 2024 crewed landing and has since slipped repeatedly, is currently aiming for no earlier than 2027. The race is genuinely competitive in a way that has not been true of space exploration since the 1960s. Let us be precise about what is really happening here, because it is easy to frame this purely as a scientific endeavor and miss the deeper strategic dimension. Water ice at the lunar South Pole, if it exists in the quantities orbital data suggests, can be converted into breathable oxygen and hydrogen-oxygen rocket propellant. Missions to Mars currently require carrying all their fuel from Earth. A lunar South Pole base with operational water electrolysis facilities could supply propellant to deep space missions at a fraction of the current cost. Mars missions could refuel at the Moon, missions to the asteroid belt, to Jupiter's moons, to Saturn's system. All of them would benefit from a lunar way station. The first country that builds a functioning lunar fueling depot does not just gain a scientific foothold. It gains leverage over the entire future architecture of solar system exploration. Every other space agency that wants to run deep space missions will have the option of using that facility, on terms set by whoever built it. The precedents for how resources are allocated, how landing zones are assigned, how access is governed, all of these will be shaped by whoever is on the ground first and stays there. This is why China's incremental, painstaking approach is not a sign of conservatism. It is a sign of strategic sophistication. They are not trying to win the race to plant a flag. They are trying to be the country that builds and operates the permanent infrastructure that everyone else will need. The winner of this era of space exploration will not be the first to arrive. It will be the last one to leave. There is a chapter to this story that goes beyond the Moon itself. Every piece of ISRU technology tested on the Moon, the oxygen extraction, the regolith construction blocks, the 3D printed structural components, is directly transferable to Mars. Every lesson learned about operating robotically in advance of human arrival applies to Mars. Every solved problem regarding long-duration human presence in a harsh radiation environment with no immediate rescue option applies to Mars. The South Pole of the Moon is not just a destination. It is a training ground, a test facility, and a proving ground for the entire enterprise of multiplanetary civilization. What works on the Moon gets applied to Mars. What fails on the Moon fails in a place where astronauts are 3 days from home rather than 9 months. The Moon is, in this sense, the last place in the solar system where you can run genuinely dangerous experiments and still get your people back if something goes wrong. China understands this. Their roadmap does not treat the Moon as a final destination. It treats it as stage 1 of a much longer arc. The ILRS is designed from the beginning to be a prototype for permanent surface installations on other worlds. The technologies being validated by Chang'e 8 are not lunar-specific technologies. They are planetary surface technologies that happen to be tested on the Moon first because the Moon is close. The question being answered by all of this is not, can we visit the Moon? That question was answered in 1969. The question being answered now is, Can we live there? Can we work there? Can we build there? Can we sustain ourselves there without continuous resupply from Earth? And if the answer to those questions turns out to be yes, if the ice is there, if the ISRU technologies work, if the construction robots function as designed, then the moon becomes the foundation from which everything else in the solar system becomes accessible. That is what China is building, not a monument, not a symbol, a foundation. Strip away the engineering and the orbital mechanics and the geopolitics, and what remains is a very simple observation. The south pole of the moon, with its water ice, its near-permanent solar illumination at nearby peaks, its scientifically extraordinary geology, and its position as the logical gateway to deep space, may be the most strategically valuable piece of territory that has ever been contested. More valuable, in long-term terms, than any oil field. More valuable than any strategically located strait or bay or coastline. Because what is at stake is not control of a regional resource. What is at stake is the operational foundation for humanity's entire future beyond the Earth-Moon system. And right now, systematically, mission by mission, from orbiting to landing, from landing to sample return, from sample return to water search, from water search to ISRU testing, from ISRU testing to permanent base construction, China is working toward owning that foundation. The strategy is not subtle. It is not hidden. It is publicly documented in their 5-year space plans and their mission announcements and their international cooperation invitations. But its full implications are only apparent when you trace the entire chain from its beginning to its projected end. When you see not the individual missions but the architecture they are collectively building. From the first Chang'e orbital missions in 2007 to the ILRS construction timeline in the 2030s, this is a 25-year plan being executed with a consistency and coherence that is genuinely rare in human institutional history. It is not the result of one visionary individual whose departure might derail everything. It is a national strategic objective embedded deeply enough in China's space program that it has survived leadership transitions, budget cycles, and 2.5 decades of geopolitical change. There will be a specific moment, perhaps a press conference, perhaps a scientific paper, perhaps a transmitted image from a hopping robot inside a permanently shadowed crater, when confirmation arrives that the water ice is there, that it is accessible, that it can be extracted and processed. When that moment comes, the conversation will change, not gradually, immediately. The question will no longer be theoretical. It will no longer be, could the moon serve as a way station? It will be, who controls the way station? And the answer to that question will depend almost entirely on who did the work, who built the infrastructure, who validated the technologies, who established the operational presence in the years before that confirmation arrived. This is the race that is actually happening, not the headline race to put boots on the lunar surface first. The deeper, quieter, far more consequential race to be the country that has built something permanent and functional on the moon before anyone else manages to do the same. China has a 20-year head start on the planning and a 2-decade track record of execution. They have never missed a major milestone. They have never abandoned a mission mid-development. They have never allowed political friction to derail a technical program. And they are moving faster now, not slower. Everything that used to feel like the end of the Apollo story, that moment in 1972 when Gene Cernan stepped off the lunar surface and humanity simply stopped going, turns out to have been just the end of the prologue. A false ending. An intermission in a story that was never really over. What is happening now is not a reprise of Apollo. It is something structurally different. Apollo was a sprint, extraordinary, heroic, technically brilliant, and ultimately unsustainable because it was built around demonstration rather than permanence. What China is building is infrastructure, Infrastructure has a different relationship with time than demonstration does. Demonstrations happen once. Infrastructure, if it is built well, lasts generations. If the south pole of the moon contains the water that orbital data suggests, and if the ISRU technologies under development prove viable in actual lunar conditions, then we are approaching an inflection point. A moment when the moon transitions from interesting scientific destination to essential operational node for human civilization's expansion into the solar system. That is not hyperbole. That is the straightforward logical consequence of what we know about the resources that may be there and the technologies being developed to use them. There is a word for what happens when a single location provides control over access, over logistics, over the supply of essential materials that every other actor in the same domain needs. That word is choke point. History is littered with examples of choke points that shaped civilizations. The Strait of Hormuz, the Suez Canal, the Strait of Malacca. Each one is just geography. Each one is just a place. But whoever controls that geography controls the terms on which everyone else operates. The south pole of the moon, if it contains harvestable water ice and becomes the site of a functioning fuel depot, will be a choke point of a completely different order of magnitude. Not for ships, but for spacecraft. Not for oil, but for the propellant and life support materials without which no deep space mission is possible. And the country most systematically working toward that inflection point, right now, today, is China. Not because they got lucky, not because they moved fastest, but because they made a plan 25 years ago, committed to it, and never stopped, step by step, mission by mission, rover by rover. They are building the future, on a surface that the rest of the world once thought was just an old, finished chapter. The moon was never a finished chapter. It was always just the beginning. If this changed how you think about the moon, please give this video a like and subscribe to stay ahead of new episodes. Don't forget to turn on notifications, because this story is still very far from over. And I really want to know what you think. If a lunar base exists by 2050, would you take the risk and go?